right, in this question, we're going to look at two gliders are traveling towards each other on a horizontal air track. Glider P has a mass of 0.3 kilograms and is moving with a constant speed of 1.2 meters per second. Glider Q has a mass of 0.6 kilograms and is moving with a constant speed of 1.8 meters per second. So this one is both faster and more massive, it's twice the mass, and a little bit more speed, right? So more momentum in glider Q for sure. The gliders have a perfectly elastic collision. What are the speeds of the two gliders after the collision? Perfectly elastic collision, by definition, means that the kinetic energy before is equal to the kinetic energy afterwards. And so a very inefficient way of solving this would be to sort of, compare the 1/2 mv squared plus the 1/2 mv squared initial equals the 1/2 mv squared plus the 1/2 mv squared, and you could sort of check each one of these and see which one adds up to the initial kinetic energy. In all collisions, momentum is conserved, but in perfectly elastic collisions, kinetic energy is conserved. Check the link there for the derivation of the idea that the relative speed of approach will equal the relative speed of separation when this is true, when there's a perfectly elastic collision where kinetic energy is conserved. Again, that idea is derived in another video. The relative speed of approach equals the relative speed of separation. And remember, to calculate relative speed, when two objects are going towards each other, right, we're going to add their speeds to calculate the relative speed. So we don't really need to consider the mass. We just have to sort of calculate what's the relative speed of approach. So it's going to be 1.8 plus 1.2, so 3. So we know that the relative speed of approach is 3. And now we can consider each of the possible answer choices much more efficiently than sort of doing the full 1/2 mv squared for each of them. 1.2. Now let's see, they're going to collide and they're going to bounce off. And so when they bounce off, they're going to be going in opposite directions. And so if we add them when they're moving in, well, if we add them moving opposite directions, they collide, they bounce off, they're still going to be moving in opposite directions, right? It's just sort of the different way each one. So that still is, sort of they're moving in opposite directions, right? So we'd still add. So 1.2 plus 0.6 is 1.8. Nope. 1.2 plus 1.4 is 3.4. That won't do. 2.8 plus 0.2 checks out. 3.6 plus 0.6 is more, but if you subtracted those, you could maybe sort of get the answer of 3 if you sort of just misinterpret, like, oh, when I added them initially, now I got to subtract them. But indeed, they'll still be moving in opposite directions afterwards. It's going to sort of bounce off. The speed of P is going to be much faster. So it's sort of like the momentum of this thing, which is more, it has more momentum, gets sort of delivered or transferred into P. And so it starts going back the other way very fast compared to this one that gets turned around, but it goes very sort of slowly back the other way. And so choice C would be correct because it's the only one where the relative speed of separation equals the relative speed of approach. You just sort of add up these velocities and add up these, and they have to equal on a perfectly elastic collision.